Good morning, everyone. In the previous class, we were discussing about the pass transistor logic, and we saw different possible combinations uh, by considering series and parallel of both kind of transistors. Either it is PMOS transistor or it is NMOS transistor. So we saw like if the PMOS transistors are in a series, in that case, we can make the NOR kind of arrangement. And if NMOS transistors are in series, then we can make the N kind of arrangement. And similarly, the parallel combination can give you the OR and NAND kind of configuration. But the important thing is, whatever the structure we have made here, this was the function of input. Like if the input will change, accordingly output will be reflected. Like suppose if input is equal to 0, in that case, like if you see the first circuit, if input is equal to 0, in that case, in any of the cases, either input is 0 or 1, whatever it is, like A or B is 0 or 1, output is always 0. Okay, in the previous three conditions, it will be in the high impedance state, because there will be open circuit, like any one of the transistor will be in open state. So if any one of the transistor will be in open state, so there will be a high impedance state. And for the last combination, like A and B is equal to 1 1, even though if V in both the transistors are on, if V in is equal to 0, we will observe output is equal to 0. Okay, so in that case, this is how this circuit will be have. Okay, so initially what we consider, because we have already a capacitor over here which is initially pre-charged or discharged, we will consider it. So this high impedance state will not play a major role to decide the logic. Okay, so this is what the structure is and how this works. Now let us talk about the something more into detail about the pass transistor logic. So how we can make the pass transistor logic, how, because see, as we know that, yeah,
where will be the impedance high?
High impedance means simply like, see, if we consider figure number 1, in this figure, if A is equal to 0,
yes,
then,
yes, sir, I understood.
So there will be no path between input and function, output function. So we can call it the high impedance state. Okay. So this is the thing. Now let us talk about more into detail of this pass transistor logic. So this is the basic structure, what the pass transistor logic look like. We have a network. So because see, in the previous diagram, we saw that we have a transistor which decides what kind of logic we want to implement. Okay, so based on the series and parallel combinations, that will decide the logic function. But because we know that the PMOS transistor is strong high but weak low, and vice versa for NMOS transistor. So suppose if I am using NMOS transistor to pass high logic, in that case I will get some threshold voltage drop at the output side. Similarly, if I am using PMOS transistor to pass logic 0, in that case I will get some threshold voltage drop. Okay, so to overcome this problem, we can have several solutions on it. So what kind of solution we can, let us try to understand those things. Okay, so here we have some network, switch network, which decides the logic based on the input pattern. This network switch can be in the series or in the parallel combination. Either it can be made of the PMOS transistor or it can be made of the NMOS transistor, or the combination of PMOS and NMOS transistor based on the circuit whatever we have, or based on the function whatever we have. Okay, so this is what we can make. So suppose I'm just making a simple this kind of pass inverter, where we have provided one transistor which can pass the logic at node X, and that node X logic will depends on the value of input. Like IN, if IN is equal to 0, in that case this will be the high impedance state, in the high impedance state. And if IN is equal to 1, in that case this VDD will be transferred to this X. But because this transistor is nothing but this is the NMOS transistor, and we are trying to transfer logic high, so there will be some drop, threshold voltage drop. Okay, so let us try to see how the waveforms will look like. Okay, so suppose I am just changing input from logic 0 to logic 1. Okay, so this is what I'm changing the input from. Initially, let us consider input was 0, and I'm changing it the output from low to high. In that case, what will be the output? Like if I'm assuming this VDD is equal to 1, then there will be a threshold voltage drop here, and this threshold voltage, this is nothing but this is the VTH drop. This is equivalent to VTH. Okay, so we will never achieve at the VDD exactly whatever the value of VDD is. So this drop is nothing but this is equivalent to the VTH drop, and this maximum voltage is nothing but this is equal to VDD. Okay, so this kind of drop we will observe. But what happens if I will keep on connecting more number of transistors? This drop will this drop will be added. Okay, and if this drop will be added, then might be after a few stages, after few cascading stages, might be there will be a sufficient drop that can flip the logic. Okay, I'm observing that the output should be high. I'm assuming that output should be high, but because of there are several threshold voltage drop, might be the logic get filled. So to overcome that problem, we need to use either buffer circuit or the inverter circuit so that it can boost the logic. Okay, so because the inverter or the buffer circuit has some noise margin, so even though it will receive, even though this inverter will receive like VDD minus VTH, so the input of this inverter is nothing but this X is nothing but this is VDD minus VTH. Okay, because we are passing logic high through the NMOS transistor. So this voltage will nothing be, this will be the VDD minus VTH. So the input of this inverter is VDD minus VTH, and which like this inverter will act like this is logic high, and accordingly it will give logic low. So we can achieve the complete swing by adding some inverter or some buffer circuit onto it. Okay, so this the output we can observe. Initially the output was 0, output was 1 because of this because the X was initially 0, and when this X will becomes VDD minus VTS, this output will become logic low. So we can achieve complete swing. Yeah, definitely we can add one more inverter here to make it buffer, so that we can have a the exact logic what we want. Okay, so we can make by connecting two inverters, we can make it buffer, and the swing will be same like whatever we are observing. Okay, so this is what the importance of passed transistor logic and how it can be achieved. Let us try to implement some of the function. Like initially in the previous circuit, what we saw, or in the previous page or previous slide, what we saw, the output was the function of input. Okay, so based on the input value, either it can act. Let me go to that slide again, and then here, if you see here, this. If you see the first figure, even though A and B is equal to 1, the output F was depends on the value of V in. So if I will change the V in from 0 to 1 or 1 to 0, might be the output will be changed. So it is not complete AND gate. We cannot claim like this circuit is completely acting as an AND gate. Now the AND gate functionality that depends on the value of V in. If V in is equal to 1, in that case it will act as an AND gate. Otherwise this will be nothing. This will pass logic 0 always. Or for three combinations, it will be in the high impedance state, means the capacitor will not be charged, so it will give logic 0. And for the fourth condition, even though both the transistors are in on state, we will get the output 0. Okay, so this will not act as a completely AND gate. Okay, so to overcome that problem, we can have some other kind of alternatives or other kind of arrangement. So let us try to see this arrangement. So what we have provided here, we have provided two NMOS transistors which are in the parallel. Okay, so these two NMOS transistors are in parallel, and one of the NMOS transistor is activated by the signal B, and the second second NMOS transistor is activated by the complement of B. Okay, and one of the terminal, like this drain terminal of the one NMOS transistor is connected to A, and the drain terminal of another NMOS transistor is connected to the grounded. Okay, so let us try to make the truth table of this one. Okay, so we will observe like A, B, and F. Okay, so if A and B is equal to 0, 0. Okay, so can anyone suggest which kind of logic it is? So if A is equal to 0 and B is equal to 0, so what will happen? If A is equal to 0, B is equal to 0, so this transistor M1 will not be activated. Yeah, let me write the M1 and M2. So this is M1, this is M2. So transistor M1 and M2 will not be activated. Okay, M1 will not be activated, and if B is equal to 0, so this B complement will activate this transistor M2. So this logic 0, whatever we have here, this logic 0 will be transferred. So this logic 0 will be transferred through this one. So I will get logic 0. Okay. Similarly, if I am considering the second stage, like 0 and 1 combination. So if I have A is equal to 0 and B is equal to 1, in that case, this transistor M1 is in on state. Okay, and M2 will become in the off state because the B complement will deactivate this transistor M2. So this transistor M1 is in on state. So whatever the logic at A is, that will be transferred to the output F. So because the A is 0, so the output will be 0. Yeah, because I am using this NMOS transistor to pass logic 0, so this will completely pass the logic. So like we will get the complete logic. Now let us talk about the third case. If 1 and 0 is there, so if A is equal to 1 and B is equal to 0, again what will happen? This M1 transistor will not be activated, this transistor M2 will be activated, and this does not depend on the function, like it does not depend on the A, because here the one of the input of this M2 is connected to the grounded. It does not depend, like this M1 transistor will be in high impedance state. So if B is equal to 0, so M2 will be in on state, so logic 0 will be passed. And similarly, if 1, 1 is there, then in that case, what will happen? This transistor M1 will be activated. And now here is the problem. Here what we will observe? We will observe output F, like if A is equal to 1, then yeah, let me assume if A is equal to VDD, okay, in that case, I will observe VDD minus VTH because we cannot pass complete logic high. Now, this circuit is giving you the perfect combination, and this is nothing but this. What kind of logic it is? Like F is equal to, this is like A into B, AND gate. Okay, so this is nothing but this is AND gate. Okay, so this is how this circuit will look like. Okay, now let us move ahead with this one. So if there is there is any doubt, you can ask the question. Because yeah, just because we are getting some threshold voltage drop for the last combination, we need to use one buffer after this one so that we can overcome this problem. Okay, now let us try to implement some of the bigger circuit. Okay, so let us assume I have a function which is A plus B into C complement, and I want to implement this with the help of NMOS pass transistor logic. So if I want to implement with the help of NMOS pass transistor logic, let us see how the structure will look like. Okay, so this is really very important to understand. Like if I am designing this circuit with the help of NMOS transistor, then how it will look like. Let us try to expand this one. So F is equal to A plus B into C complement. Okay, And if I expand it like just De Morgan's theorem, I have to apply it. So it will become A plus B complement plus C complement. Okay. Again, if I apply the De Morgan's theorem, because this all the transistors are not individual, like all the variables are not individual variables. So I need to break them. So that will become A bar dot B bar plus C bar. Now all the variables are uh, individual one. Okay. Now the question is, because I am implementing this particular logic with the help of NMOS pass transistor logic, and we know that if there is some dot symbol, in that case we already know the things, like if there is some dot symbol, I need to put them into the series. Okay, I need to put the transistors into the series, and if there is plus symbol, then I need to put the transistors into the parallel combination. Okay, and because I am using NMOS transistors, so I need to use the logic, whatever the variable we have as it is, so I don't need to complement it. Okay, so in that case the structure will look like, I need to keep two transistors that will be in the series. Okay, so okay, so these two transistors are in series. Now I need to connect, well, yeah, this will be like A complement, this will be like B complement, and I need to keep one transistor that will be in the parallel, and this will be nothing like C complement. Okay, and this is how, like here I need to provide the input, and here I will get the function output. Okay, so this is how we can implement with the help of NMOS logic, and this is the structure of NMOS pass transistor logic. Similarly, if someone can ask like how we can implement the same logic with the help of uh, PMOS pass transistor logic. Yeah, let me compare a few more things. Okay, so let me design the same thing using PMOS PTL. Okay, so if I am using the PMOS PTL, in that case, how we can design? We can simply design, because for the PMOS we need to use a different kind of logic, like the complement of it. So the combination, or it will be like same only. So this is how this will look like. Okay, so this is the input, and from here I'm getting the output F. Now here we have, because this NMOS and PMOS are complementary to each other, so the input here will be like A, B, and C, because I have bubbled them. Okay, so this is how the structure using the PMOS PTL will look like. Okay, now there is some let us compare a few things. Okay, so if, let us assume, if I am designing this function with the help of CMOS circuit, so can anyone comment how many transistor we need to implement this one?
So 6 transistors.
6 transistor will be needed to implement this function if I am using this CMOS based circuit. Okay, now if you see this first circuit, how many transistors we need to implement this one?
3.
3 transistors, but we also need the complement of the inputs, whatever we have. We need the complement of variables, not the only like A, and if I have the A, B, and C inputs, so I need to first complement them, then I need to use it. Okay, so here a complement of A is needed, complement of B is needed, and complement of C is needed, and for that purpose I may need 2 transistors each. So 6 transistors for complementing and 3 transistors for this function. So total number of transistor will be 9 transistor. Okay, because if I have the input like A, B, and C, I will tell you then what is, like someone may ask, then what is the benefit of this pass transistor logic? I told you before, this pass transistor logic is utilized when we want to reduce the number of transistors, but there is some contradiction. What is that contradiction? I was saying, like initially for the CMOS based logic, I need 6 transistors, but from this implementation, I need to use 9 transistors. So how to overcome that problem? This is not a solution. This becomes a problem. It is the area is going to be increased. Okay, so let me tell you what is the solution for that one. I will tell you in detail. No problem at all. So if I'm considering like this A, B, and C, and to implement the complement of this A and B and C, I need to use inverter, and by considering those things, so total number of transistor will be the 9 transistor. Now let us talk about this second circuit. If I'm designing the same logic with the help of PMOS transistor, then we will get like only we require only 3 transistors. Okay, so three transistors will be needed to design this one. Okay, so here we can save the area. In this case, we can save the area. You need to check the functionality, how this function will look like, and then accordingly you can make it. Okay. Yeah, so I just told you, if I need to implement the complement of any variable or any input, in that case the area is going to increase. So how to overcome that problem? That problem will be solved in the next slide. I will tell you. Okay. So before going into the problem of this logic or number of transistor increment due to the complement logic or due to the like inverting logic, let us try to come up with some of the problem. Like I was saying, there is a problem of threshold voltage drop. Okay, threshold voltage drop will be there if we are not passing the exact logic. Like if I have the PMOS kind of the pass transistor logic, in that case high logic will completely will passed. But if I am passing logic 0 through the PMOS transistors, then that will create some problem. There will be some threshold voltage drop problem. And similarly, if I have the NMOS transistor and I am passing the logic high through the NMOS transistor, there will be some threshold voltage drop. We know these things. Okay. So to understand this one, let us try to consider some few more things. Like suppose I have connected 2 transistors in a series, in a way, something like this one. Okay, so first transistor is here, like the input of this transistor M1 is like gate is connected to B, and the one other terminal is connected to A. So if you see here, this X is nothing but this will be like, let us assume A is equal to VDD. Okay, so or B is equal to VDD. So I have provided B is equal to VDD, and also this A is equal to VDD. Okay, so this X is nothing but this will be like VDD minus of VTH. Okay, so this Vx is nothing but this will be VDD minus VTH. Now if you see, the gate terminal of this second transistor is not now, it is not now VDD, it becomes the VDD minus VTH. Okay, so the output voltage, like we will observe the output voltage across this at the point Y. So because this gate terminal voltage is VDD minus VTH, okay, and because if the C is again VDD, so what I will observe? I will observe this VDD is not just like there will be some 2 threshold voltage drop, because the voltage at the gate terminal of the second transistor is not exactly VDD. This is VDD minus VTH. So let us assume this is the VTH1. So at this point, what I will observe VDD minus VTH1 minus VTH1. Okay, minus VTH2, which is the second threshold, the threshold voltage of the second transistor M2. So the output what we will receive at Y will be VDD minus VTH1 minus VTH2. Okay, so if we have more number of transistors which are cascaded in this way, will reduce the threshold voltage, and might be this will create the problem. Even though this, like, let us assume there is a 4 or 5 transistors which are connected like this. So even though I have connected the inverter or the buffer at the output, that will not work. It will not give you the perfect logic. Okay, so this will create some problem. Okay, so the swing at Y, output Y will be like VDD minus VTH1 minus VTH2. So this is not a good solution or good circuit design techniques. So to overcome that one, we need to consider, like, suppose let us we have this circuit second arrangement where I have connected the source and drain of the two transistors at node X. Okay, instead of connecting the source terminal of the transistor M1 to the gate of the M2, I'm connecting the source of M1 to the drain of M2. Okay, and then I'm making it X at node X. So in that case, what I will observe, whatever the X is there, like, because B and C, these are VDD. Okay, so will this output Y is nothing but this. We will always achieve, like, if I'm considering the threshold voltage of transistor M1 and M2 are VTH, so I will observe VDD minus VTH always. So the important thing is it is always preferable to use or to connect the transistor in this arrangement, not the first kind of arrangement. So to overcome the problem with the first arrangement, we can go for the second one. Okay, now, but still I'm seeing some problem here. There is a threshold voltage. Let us assume I have not connected the inverter at the output to make the proper swing. In that case, what I can do, there is a solution, and that solution is the level restorer. Okay, what is this level restorer? Let us try to see. So suppose I have n number of stages and n number of transistors which are connected in the cascading structure, cascading way. So there will be a threshold voltage drop. So the next logic should not, because if there is some threshold voltage drop, because the input will become less, for, let us assume the input for this inverter will be less, so this drivability will be decrease. Okay, so there may be some delay increment. So to overcome that problem, we can use the lever restorer circuit. And what is that lever restorer circuit? Let us try to arrange here. So if, because at this node X, we are observing VDD minus VTH, and at node Y, we are again observing the VDD minus VTH. Okay. So if I want to restore this voltage at node X, then what I need to do, I just need to connect a lever restorer, and this level restorer is made of the strong kind of logic, like, because a PMOS transistor is strong high. So yeah, I need to use it in the opposite way. Okay, so this kind of logic I need to use. I will connect to the VDD. Now this is the PMOS transistor, and this PMOS transistor will be connected by this one. So this PMOS transistor, whatever we have connected to the node X, that will be restored. Okay, so okay, so let us see how this will restore. Suppose this X is equal to VDD minus VTH. So I'm assuming that this B is equal to VDD, A is equal to VDD. Okay, so if this is the case, A and B both are VDD, in that case this X is nothing but this X will be VDD minus VTH. Okay, VDD minus VTH, because I am trying to pass the logic high through the NMOS transistor, which will give you the degraded output. Okay, now because this VDD minus VTH will be the input of this inverter, whatever I have connected. So this inverter will give logic 0, and if logic 0 is there, this logic 0 will activate this transistor, PMOS transistor, whatever we have connected here, which we are calling the level restorer transistor. So this level restorer transistor will be activated, and because this is activated, this VDD will be transferred to this node X, and then this node X will be pulled up to the VDD. Okay, because this PMOS transistor is strong high, and that will pull up the logic at node X. Okay, so this is how we can restore the logic. There will be no threshold voltage drop. Okay, so this transistor we call it the level restorer. Okay, so level restorer transistor. Okay, but the problem with this logic is like if I have the this is going to increase the number of transistors. Like we need one inverter and one PMOS transistor to design a level restorer circuit. So suppose if I have more number of NMOS transistors are in cascading like this one. So if I have more number of transistors are in cascading, so for each node we need an individual level restorer arrangement, and that will lead to the area penalty. So yeah, definitely this will improve the noise margin, because this is restoring the logic to the original value. So this VDD minus VTH will be increased to VDD after using the level restorer circuit. Okay, but the problem is like it will require more number of transistors, and the area penalty will be there. Now, so this is the solution, and again one problem comes. So the second problem will be solved. But yes, the first problem is still unanswered. That problem was like if I'm designing some circuit with the pass transistor logic, then like in the previous figure, if we see here we need 9 transistors to implement the first figure. Okay, and which required more area as compared to CMOS. And the objective of this pass transistor logic was to reduce the number of transistors. And this problem is not we are not able to solve this problem. So let us try to see how we can solve this problem with the help of this one. So to solve that problem, we have a different kind of pass transistor logic arrangement, and we call it the complementary or differential pass transistor logic. Okay, so complementary or differential pass transistor logic is how it works. Let us try to see. For the complementary or the differential pass transistor logic, we need to create two kind of network. One is the actual pass transistor network, whatever we have designed, and the second one is inverse pass transistor network. Okay, and if the input of pass transistor logic is like A, B, C, so the input of inverse pass transistor logic will be like A complement, B complement, C complement, something like that. So in that case, we will get the two different kind of functions, like function and its complement. So at the output, we will receive two kind of outputs. One will be the function, and the second one will be the complement of its function. Okay, so what is the solution? What is the benefit of this one? The benefit of this one is like because we are now the circuit is differential, so we can get both kind of logic, the actual logic and the complement element of it. So we don't need to design an individual circuit for both the one. Like if I'm designing AND gate, so I will get by default NAND gate. Okay, so AND and NAND structure will be designed. So I don't need to create a different kind of circuit for the NAND arrangement if I have designed the AND arrangement. Okay, so this is the things. So let us try to have some circuit like this. So let us assume I have a 2 transistor. Okay, so here I have transistor like the first structure, like first 2 transistors are the pass transistor network, which they are giving like AB. The function is AB. So and the input of second structure, which is the inverse pass transistor logic are A complement and the B complement, and based on the inputs whatever we have provided like B and B complement, this will give like AB complement output. So if you see here, this if I will use a single block, this particular single block, in that case this is nothing but this can act as a AND gate, and if I will use this block, this can act as a NAND gate. Okay, so with the help of both the things like AND and NAND logic can be utilized. So now if you see here, if by this with the CMOS inverter, if I need to use NAND and both, in that case what I need to do, I need to use the first I need to design the NAND gate, then I need to invert it. Okay, and then I will get it. So but here I will get the differential kind of arrangement. Both the logics are there, and even though the delay is also approximately equal here. Okay, so like I will get the output F and F complement at the same time. Okay, at the same time means the delay will be equal, like the single transistor delay will be there. But in case of the CMOS structure, let us assume I just want to design the AND gate. So what I need to design, I need to first design the NAND gate. Okay, because in the CMOS structure, I cannot design the actual logic. I can design the inverting kind of logic. So NAND gate I need to design, and then I need to connect the inverter here to make it the AND gate. Okay, so the delay of AND and the NAND will be different. So there will be one more additive delay for this inverter if I'm considering the CMOS based logic. Okay, but here what I will get like because to activate this one I need to use the B complement. So I'm assuming the A complement and B complements kind of inputs are already available with us, and so in that case for F and F complement the time will be same, so delay will be equal. Okay, so this is how we can make the function symmetrical. So this is what how we can make the AND NAND logic. Similarly we can design by changing the input with some other way, like by giving AB and A complement B complement, and if I interchange these values with the B bar and the B, like here we had the gate controllability with the B and B bar, and here we have the B bar with the B, then we can make the same circuit as a NAND and AND structure. Okay, so what is the importance here? Importance is like if somehow I interchange this gate controllability, the same kind of circuit can be utilized as a NAND and NOR gate. Okay, so this is the importance. Like a small programming is needed, like a small controllability is needed at the gate side, and by doing so we can utilize the same circuit either like a NAND NOR or AND OR structure. So like reusability is more here. So by utilizing this complementary or differential pass transistor logic, we can make the same circuit more reusable. Okay, so the reusability is more here. But if the same kind, like if I have to design like a NAND gate and NOR gate and AND gate and OR gate in the CMOS based logic. So the reusability is not possible. We need to separately design the NAND gate and separately design the NOR gate, and then we need to complement those functions and we can utilize it. Okay, so this is the problem with the CMOS, and this problem is overcome by this complementary pass transistor logic, or CPTL, or DPTL, anything you can say. Okay, so this is the really very important. Similarly, we can design some other circuits as well, like by changing the input in this way, like if I am keeping the B bar and B just like this only, and if instead of B here, if I'm replacing this B with the A bar and A, so here we had B and B complement, and I am replacing this B with the A bar and this B bar with the A. So the same logic can be utilized as a XOR and XNOR logic. So this is really very interesting to understand this kind of logic, like a small change either at the gate side or at the source or drain side, we can utilize this same circuit for the different kind of logic functions. Okay, so the reusability is more by using this complementary or differential pass transistor logic. So this is what we have made here, like by using the NMOS transistor. Now the homework is design all these circuits like AND OR gate and other things like NAND, NOR, and or XOR and XNOR logic with the help of PMOS transistor. So this is the homework for you. Just do it at your home. Okay. So this is all about the complementary. So the problem which we had, like more number of transistors is needed even in the pass transistor logic. Now this is solved by with the help of this differential pass transistor logic. Okay. Let us talk about few of the techniques how we can design the robust and efficient pass transistor logic. Yeah, so there are few techniques to design the robust and efficient pass transistor logic. The first technique is the level restorer, which we have already studied before a little bit. The second one is the multiple threshold voltage transistors, use of multiple threshold voltage transistor. And the third solution to overcome this problem is the transmission gate logic. Okay, so these are the three techniques that can be utilized to design a robust and the efficient pass transistor logic. Okay, so let us discuss one by one. So the first solution is the label restoration. How we can restore label, like just the node at which we need to restore, what I have to connect, I have to connect one inverter, and then that inverter will control the PMOS transistor. Okay, so that inverter, like, yeah, here we have the circuit. So suppose I have this logic, this inverter, this transistor I have, where I have the A and B, and I want to restore this particular logic. Okay, this node X I want to restore. In that case, I will use one inverter, and then inverter will control this transistor MR, which is the label restorer. Okay, and by this way we can restore it. So we have already studied this one. I have already explained this, how it works. Okay, so based on the input and output combination, like if B is equal to 1 and the A is equal to 1, in this case I am assuming, like, yeah, 1 means the VDD. Okay, 1 means I am saying VDD. So if A and B both is equal to VDD, in that case this X will become VDD minus VTH. So because this inverter will act as a, this will convert this VDD minus VTH into the logic 0, and that will activate this MR, and then this node X voltage will be restored with the VDD. Okay, but if the A is equal to 0, okay, so if A is equal to 0, in that case the VDD B is equal to VDD will activate this transistor MN, and this X will be 0, and if X is equal to 0, output of this inverter will be 1, and this MR will not be activated. So there is no impact, because I'm just passing the logic 0 through this NMOS transistor, so that will not create that much problem. Okay, so this is how we can utilize it. Yeah, we can also get the output from here also. So we can take the output from here as well. So V out complement. Yeah, let me make it perfect. So the output can also be taken from here, and that will be out complement. Okay, so this is what we can do it. Okay, but the problem is like, if the sizing of this MR is varying, okay, so if the sizing of this MR is varying, in that case the voltages will also vary, like it will create some problem. The voltage at Vx will be changed. Okay, so initially, like if I have the lower values, like initially if the transistor sizing is not that much strong, if it is weak, then the voltage will look like these ones. Like the initially, let us assume it was high, so this will change something like this. This is not exactly Vx, this is the V output at this one. So if I'm increasing the sizing of this MR, then might be the waveform will change, or it will shift somewhere towards the upward direction. So this output will, like, the based on the strength of this MR, okay, this output voltage, yeah, this is not Vx, yeah, there is some typo here, this is not Vx. This output voltage will shift in this particular direction. So this is nothing but this is the W by L of transistor MR. So by changing the W by L of transistor MR, this output will be changed, because if it is more stronger, like, see, if it is more stronger, in that case, like this will try to keep it, this will try to hold the logic, like, so it will try to hold the logic. And this, yeah, of course, this is Vx only. So this, like, if the MR is more stronger, in that case this Vx voltage will be very high, like it will be more stronger, and it will take more time to discharge this one. So this will hold tightly, and if this is very small one, then the logic can be changed from 0 to 1. So the swinging, like switching between 0 and 1 at node X, that depends on the level restorer as well. So this play a major role on this one.